Alright guys, so finally the time has come and today we are going to cover dynamic programming. I know that you have been waiting for this day for a while, me too, and I'm so glad we are doing it now. So, what is dynamic programming? Let's start with understanding what the idea is all about. So, dynamic programming is simplifying a complicated problem by breaking it down into simpler sub-problems in a recursive manner. That's the first step. In order to solve the problem, we are going to divide it into sub-problems. And these sub-problem solutions are going to be useful in constructing a solution for a larger problem. So, that's exactly what we do in the second step. And one trick, one gotcha, which is we actually save the results of these sub-problem solutions so that if we want to refer them again, we can just use the result directly rather than going all the way down to the base solution, constructing it again. So this actually brings the efficiency of dynamic programming. Like basically after you do one thing once, you save the result. Whenever you need the same thing again, you just go there and then you take it from there rather than calculating it again and again. So, how can we detect whether a problem is a dynamic programming problem or not? Like most of the time, typically, dynamic programming is applied to optimization problems. Meaning, there are many solutions with values, like we are either trying to maximize that value or minimize that value. And we are looking for an optimal solution. We are not just looking for a solution, we are looking for an optimal solution. But at the same time, it doesn't mean that there is only one optimal solution. Like there can be many optimal solutions, perfect results with the same score, but they can be different from each other. So, like it's an important difference. With dynamic programming, we can go to one of the optimal solutions. And there is no guarantee that there will be only one optimal solution. There can be more than one. So, with examples, it's going to be more clear, as always. Our first example is a very simple one. Let's think about Fibonacci. Is the code readable or should we put it on the whiteboard? Maybe it will be better to put it on the whiteboard. So let's quickly remember how we calculate Fibonacci numbers. So let's work with first 10 Fibonacci numbers. We start with 1, 1, and then 2, 3, 5, 8, 13, 21, 34, 55. So, like the first thing that we should do when we face with such a problem is we should recursively define the solution depending on the sub-problem solutions. So when it comes to Fibonacci, how can we do that? Let's take a look at Fib_n. What is the definition of Fib_n? Let's try to come up with the full formula. So with recursive definitions, there are two things that we should take care of, right? First, we need to define the recurrence relation so that we know how to define Fn based on sub-problem values. And the second thing is we need to decide where we should stop, which is our base case. So in case of Fibonacci, what is our base case? The first two numbers are 1, right? So we can say if n is less than 3. Actually, we don't need if for the mathematical description. Our solution is just 1. And if that is not the case, n is greater than or equal to 3, Fib_n is equal to Fib_n minus 1 plus Fib_n minus 2. So, now we have the recursive definition of the function. And so the thing that dynamic programming is helping us is when we save the solutions of the sub-problems in some place, like we mentioned about this in the early days, right? We call it memorization. So that's like one type of dynamic programming, one part of dynamic programming. Once we do that, we don't have to calculate these results again and again. So now let's take a look at the tree of fib n. Like let's say we want to calculate fib 5. By this definition, which sub-problem solutions fib 5 is going to look for? Fib 4 and fib 3. How about fib 4? It's going to look for fib 3 and fib 2. And again I have fib 3 called here, like which is still greater or equal to 3. Therefore, this is going to call fib 2 and fib 1. And these are trivial, so they are going to be our leaf nodes. And here for fib 3, we need to have this branching as well. Like basically, if we just define this code recursively without thinking of saving our sub-problem result in some place, what is going to happen is we need to visit all these nodes in this tree, right? And how much of a repetition are we doing here? So let's try to see like the first call of each value. Fib 5 is here, fib 4 is here, fib 3 is here, fib 2 is here, fib 1 is here. So all the other nodes that are not ticked, basically, they don't have to be calculated again and again. So this one, this one, this one, this one. Like you can think of these guys are trivial because they are the base cases, that is true. But what will happen when I add fib 6 over here? And I'll have this whole tree again here, right, for fib 4. So you can actually see just in couple levels going up, there will be more and more repeated sub-problem calculations. So that's why dynamic programming can actually save us a lot of time in such cases. Because if total number of sub-problems that we need the solution of to construct the larger solutions is polynomial, then by applying this principle, meaning calculating one sub-problem result once, saving it and using it from there, instead of recalculating it again and again, we can solve exponential recursive solutions into polynomial dynamic programming solutions. That's why it's a very powerful technique and used in many different disciplines. So, are you guys able to see the code piece over here, or should I write it to the whiteboard?
You can see.
Okay. So let's start with the recursive definition of fib function here. Let's assume the result is going to fit into an integer, and we take n. Our base case is if n is less than 3, we are going to return 1. And if this is not the case, we are going to return fib n minus 1 plus fib n minus 2. So, in this code piece, are we doing anything to not calculate the sub-problem results again and again? So what is going to happen eventually if I call this with fib 11, for example? Like it's going to calculate fib 5 maybe, I don't know, 100 times. Right? And this is something that we can easily avoid, right? What was the first method to avoid this sub-problem solution calculation repetition? What was it called? Memorization, right? And the idea is very simple. Basically, once we calculate a result, we save it. And whenever we are supposed to calculate the value, we just check whether it was calculated before or not. So now let's do the modification to this code. So here, what we are going to do is, the base case check is going to stay as the same. And if we get to here, it means we need to do some calculations. And here we are going to check if fib, and let's say we put it into fib array. If fib n is greater than 0, let's say initially it has 0 values. Then what we are going to do is we are going to return fib n. No need to calculate the solution for this subproblem again. It had already been solved. And the result was already saved in the fib array. So I can just return it from there directly. And if this is not the case, what am I going to do? I'm going to return fib n. But first I have to calculate it. Fib n minus 1 plus fib n minus 2. So is this clear to everybody what we are doing here? With the help of this, what is going to happen is, once we try to calculate the value of fib3 again, we are not going to dive into its subproblems anymore. Because we already know that it was calculated here and saved. So therefore, we are going to get the result directly rather than calculating it again. And in case of calculating fib6, since fib4 was already calculated here, likewise, we are not going to dive into subproblems of fib4 here. We are going to use the result that we calculated from previous subproblem solutions. It was already calculated once. We are still living in the same world. No point to solve the same subproblem again and again. And like this is actually top-down approach. Meaning, when we want to calculate fib n, we start from the top and then we continue diving into subproblems until we hit to the base case or a subproblem that had already been solved and its result was saved. And after that point, we get that result, and by using such subproblem results, we construct a larger solution. And then we return it back. We give it back to the upper covers. And eventually, like it comes down here, 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 and then goes back up here, 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 and then it returns back. So this is called top-down approach. We start from the top, we go to the down. There are some advantages and disadvantages of top-down and bottom-up approaches. We are going to get to that in a minute. But before we go, I also want to show you how the bottom-up approach would work for Fibonacci. So, I mean, as the name implies, in the bottom-up approach, we are going to start from the base values. What are our base cases for Fibonacci? 1 and 1, or like first and second element, right? So that's where we are going to start from. So let's say this is top-down. And here we are going to have bottom-up Fibonacci. And again, I assume the result is going to fit into integer. So, this time, we are going to fill up our fib array within the function. It's not going to have any recursive calls because we are doing things the bottom up. Let's say we support up to max n. And let's assume I can just initialize it like this, with all zeros. And the first thing I should do is I should set my base cases, right? And my base cases are fib1 is equal to, fib2 is equal to 1. Yes?
It's not clearly visible. Maybe a different.
Maybe a different, sure. Up to this point, is it clear, or maybe I can just do this? Like it's just, we just define the array and then we initialize the first two elements with 1. Because this is our base case. And after that, we are going to have a for loop. I this time starts from 2. Because 3. 1 and 2 are already set, right? It starts from 3. And as long as it keeps going up to n, I need to calculate values. And inside I'm going to say fib I is equal to, the same with my recurrence relation here. Fib I minus 1 plus fib I minus 2. And once I get here, fib n is already calculated. So we can just return fib n. Like this is dying too, unfortunately. We started with green, continued with blue, finished with red. Okay. So is this clear to everybody? Yes.
Do we need an array of size on? Can't we just have previous, next, and count?
I mean, yes. If you want to optimize it, you can do it that way because you only need 2 previous values, so you can use the same place. But it's just like right now we want to focus on the logic part, right? Not compute efficiency. Okay, Murat, is this clear?
Yes.
Okay. So, now let's take a look how we are going to create a dynamic programming solution. So, the first thing we should do is to characterize the structure of an optimal solution. What does that mean? If we look at the Fibonacci example, this is how we are going to write the recurrence relation for solution of n. And in Fibonacci, we know that fib n is defined as fib n minus 1 plus fib n minus 2, right? So if we want to think about another easy problem, we can think of factorial problem. How about factorial n? How is factorial n is defined?
From n minus 1 up to 1.
N times factorial n minus 1, right? If we think of the recurrence relation. The definition is going to be like this. So the first thing we should do is this. And then we should recursively define the value of an optimal solution. Meaning, we start from n, and then recursively we are going to make calls for our subproblems. N minus 1, n minus 2, n minus 3, and so on. We don't know which ones are needed. There can be some problems which are skipping some of the subproblems. Like in the case of recursion or Fibonacci, we don't skip any of the subproblems. Like n requires n minus 1, n minus 1 requires n minus 2, and so on. But there are different types of problems in which some subproblems can be skipped. Like fib n, not fib n, but like fn might depend on fn minus 2 and fn minus 4, for example. In that case, n minus 1 and n minus 3 subsolutions are not going to be used. And after that, after we hit to the base, we are going to calculate the value, and then we are going to bring it back up for the top-down approach. And if we are using the bottom-up approach, then we are going to start from the base case, as in here, and then continue constructing the solution up to the desired problem level. So any questions about how dynamic programming algorithm creation works? Is this clear to everybody? So, now let's consider, let's compare these two different approaches. The bottom-up approach, or it is also called as tabulation. You basically create a table and then fill up all the fields in that. Or the top-down approach, which is also called memorization. In the bottom-up one, we have it here. We basically start from the base case, and then we continue constructing larger solutions depending on the small subproblem solutions. But as you see, like with this approach, we are filling up every single entry in our table. And in the second approach, in top-down approach, what we do is we start from the top. This time we don't care about the real solution at the beginning. We care about the recurrence relation. We care about how we are going to get to the solution. And then we start from the top, and then we call our sub-problem solvers. And these sub-problem solvers, until they hit to the base case, they will continue calling some other sub-problem solvers. And once we hit to the base case, we are going to get the result from there. And after that, by using these results, we are going to construct the solution for low-level sub-problems. And then these solutions are going to be put together, they are going to be reported up, and this way we are going to come back to the top caller. That's how we are going to calculate the solution. So are both approach clear to everybody? Top-down and bottom-up. Because there are different scenarios for which one of them can be more proper than the other. That's why we want to feel comfortable with both of them. So, let's take a look another example of bottom-up approach to make things more clear. So what was it? It starts from the solution of the base case and constructs the larger problem solutions as we go. So another example was factorial for dynamic programming, right? And what is the base case of a factorial? 0, right? 0 factorial is 1. We know that. And after we set the base case, all the upcoming cases of all the larger problems, they can be calculated based on previously solved sub-problem solutions. So 1 factorial, it is going to depend on the result of 0 factorial. 0 factorial times 1 is going to be 1 factorial. 1 factorial times 2 is going to be 2 factorial. And so on. Once we go up to n, we will be able to calculate all the factorial values. And by using this DP array, we can return any kind of factorial codes in constant time. So in the bottom-up approach, usually what we do is like we solve all the sub-problems. Like we basically populate all the values. And whenever a value is asked, then we just go ahead and return it. So that's why usually in such cases, like it's gonna work, like it's gonna do the pre-computation at the beginning to calculate all the values, and then we are gonna return the desired answer based on given n. But in the case of top-down approach, some of the sub-problem solutions can be skipped. Meaning, we don't have to calculate everything from the beginning. Once n comes in, then we can start calculating up to that value. So, if we take a look at this top-down factorial code, since our base case was 0, when x is 0, we just return 1. And if, like, assume the DP array was initialized with -1s, if the value inside is not -1, then we can just return the value, because that sub-problem was already solved before. I have the result, that's why. And if that is not the case, I have to calculate the solution. And I use my recursive formula to calculate the solution. So, now let's compare these two approaches, bottom-up approach and top-down approach, based on some criteria to get to know under what circumstances one is better than the other. Like this one is important because the choice you make can make coding easier, can make coding harder, can make execution faster, can make execution slower. So that's why it's an important trade-off, and I want you to understand this comparison very well. Let's start from defining our state as well as how easy it is going to be to move from one state to another. Most of the time, with bottom-up approach, it is difficult to define the state transitioning, because basically we are trying to look for a recurrence relation from opposite perspective. That's why it is harder. Like once I say how would you define fib n, it's very easy to say, oh, I'm going to just sum fib n minus 1 and fib n minus 2, right? Like logically speaking, it is very easy to understand. So that's why with top-down approach, modeling the state changes is going to be easier than the bottom-up approach. But as you gain more experience, defining state transitions in bottom-up approach is going to be easy as well. Like basically you are going to get to point if you can do it with top-down approach, you can also do it with bottom-up approach. But to get to that level with some complicated DP problems, you need some experience. At the beginning, modeling state transitions with top-down approach is going to feel easier. And once we look at the code that you produce in the end, right now, obviously, once you look both codes, like it's going to be trivial enough that you're going to be like, oh, both are very readable, both are very easy. But once it comes to more complicated dynamic programming problems, it is usually harder to read the bottom-up approach codes. And it's actually because of the first reason. Since state transitions are not super easy to understand in comparison to top-down approach, the code is going to be a little harder to read and harder to reason about. And the third criterion that we are going to check is speed. So when it comes to speed, there are actually two things that you should consider. First off, if you need to solve all the sub-problems, in that case, bottom-up approach is going to be more performant. Can somebody tell me why? Like, what is the overhead are we getting by the top-down approach?
We just check in a dictionary if the value exists or not, or in this case at least.
We need to check in a dictionary, yes, but I mean, we can think of this as constant time. That's one of the overheads, but there is one more dominating factor which adds the extra cost.
Recursion?
Yes. Since we are using recursion, we are actually using the call stack. And call stack is very useful, but like anything else in life, it doesn't come for free. Therefore, once we use recursion, we should be aware that our performance is going to be slightly slower than the bottom-up approach. But don't forget that this is the case when we are solving all the sub-problems. Because there is one advantage of top-down approach when it comes to speed, which is if the problem that we are dealing with is not requiring solving all the sub-problems, in that case, basically we can skip the ones that are not needed. Therefore, instead of calculating all the sub-problem solutions in the case of bottom-up approach, top-down approach can skip the unnecessary solutions for the sub-problems whose solution is not needed to construct the larger problem solution. Is this clear to everybody? Because that's an important difference. And just to summarize, if we need to solve all the sub-problems, it's faster to go with the bottom-up approach in terms of performance. But if we can skip some of the sub-problems, depending on the nature of the problem, then top-down approach can actually work faster by skipping calculation of unnecessary sub-problem solutions. And the last criterion is progress. How does the progress happen? It's also related with speed. Once we use the bottom-up approach, we need to fill up all the cells. Like there is no escape because like we construct from the beginning. We know maybe where to end, like if n is given. But up to that point, we basically need to solve all the sub-problems to reach that point. But when it comes to top-down approach, we don't really have to do that. Because we actually know which sub-problem solutions are needed, right? Because we start from the one that we want to solve. Therefore, if it is possible to skip some of the sub-problems whose solution is not necessary to calculate the larger problem solution, then the top-down approach can actually skip them. So, now let's look at the conditions of dynamic programming. Under what circumstances we can actually apply dynamic programming. So, we care about two criteria. The first one is optimal substructure property. So, do you remember it from anywhere else? From greedy approach, right? So for greedy problems, we actually needed optimal substructure property as in the case of dynamic programming. And what was it? Let's remember that optimal solution can be determined from the optimal solutions of subproblems. Meaning, if a solution is optimal, it is subproblem, so its sub-solutions must be optimal for corresponding smaller problems. And the second criterion is overlapping subproblems. When a recursive algorithm revisits the same problem over and over again, it has overlapping subproblems. I mean, we look at Fibonacci, for example. It's very obvious that there are overlapping subproblems, right? Therefore, calculating one subproblem solution once, keeping it in our memory and then returning from there as needed is gonna fasten the process rather than going ahead and calculating those subproblem solutions again and again. So what is the advantage of dynamic programming then? The advantage of dynamic programming is to solve each subproblem once, store the solution somewhere, and do not recalculate it again and again. That's the advantage. So now we are going to look for another problem. We are going to try to solve this problem all together. It's an old problem, and the first dynamic programming problem that I have seen in my life. That's why I wanted to bring it from 1994. I didn't see it at that time, don't get me wrong, but like probably I have seen it in 2003 or 2002, I'm not sure. Like 18 years ago. Now I feel like a dinosaur. All right, so now let's look at the problem. It basically asks us to write a program that calculates the highest sum of numbers passed on a route that starts from the top of the triangle, which is 7, and ends somewhere on the base. So basically, we are going to start from the top and we are going to find a way to the baseline. And at each step, we can either go diagonally down to the left or diagonally down to the right. Meaning, if we start from 7, we can either go to 3 or 8. If we are at 1, we can either go to 7 or 4. If we are at 2, we can either go to 4 or 5. So is this clear how the problem is defined? And it is asking us to come up with the highest summation from a path that is valid with the given moves. So let's think about it for a minute. Yes. What's that? You have a solution. Okay, so let's give some time to everybody to think about it and then for a minute. Feel free to use pen and paper. How many people have a solution in mind? Can I see hands? A little more. Suha, do you hear us?
Yeah, I'm trying to follow him.
Okay, take your time. And if you have a solution in mind, so please try to refute it. Now it's your time to come to the board and tell us about your solution.
So basically we use a bottom-up approach and start from the second last row of the table. And then we check from its left and from its right, and then we store the maximum sum of the element and one of its children. For example,
Where are we storing it to?
on itself.
On itself. So we update the value on itself.
Yes.
Okay.
2 and 5 is, for example, 7.
Yes.
And 7 and 5 is 12. And we do the same. Then we go up one step, and then we do the same until we get to the top, and then we have the maximums.
Yes. So now let's also do time and space complexity analysis.
Since we're visiting each element once, it's ON, and space it's O1 because we're not using any additional memory.
Uh-huh.
What else is there?
I think that's it.
Yeah.
Thank you very much. It's not that easy. Now we want to see the implementation. Because the seat is very comfortable, I'm going to keep you up.
What kind of data structure are we going to be using?
Let's say it's passed in like two-dimensional vectors, like vectors of vectors.
So,
You can delete everything on the board. So is everybody clear with the solution, by the way? Because like, is there a point not to get the maximum elements when we are in the last second row from the last row? Like for example, is there a point to connect 2 with 4 instead of 5? No, there is no advantage of that. So that's why we can add that edge. And once we do it for all the numbers in the second last row, basically it means we are going to have one less row in the whole triangle, right? We can get the new values and treat this as if that's our new triangle that we need to solve. And apply the same strategy. Get rid of the last row, get rid of the last row, until we are done with all the rows. Yes?
I'm going to assume you're going to be, the input is going to be an n by n vector. Is that
Sure,
okay?
yeah, definitely. Like just to make things a little easier here, I'm going to put it in that format. So we assume the input is passed in this two-dimensional vector or array, like whatever.
Just checking this because this way is not
We go through my implementation. We go through beginning from the second from last table row in the table. We go through every element in that row, and then we update the value of that specific row and column to the. Oh, sorry, I made a mistake. You have to submit everyone.
Hopefully these are getting better.
How do you present isso tipo possível racional que não deveria estar ada nggak main soalnya list bisa.
So for each element in that row, we update the value in that row and column. The maximum of the two elements beneath it, and its own value. And then we do that until we reach the first row, and by then we have the maximum root from top to bottom.
So do you mind executing it over the numbers so that we will also understand how it works from the example? Like
So-
you can just update everything, like because you are doing that.
So we start from 2 here, and then we select the maximum from 4 and 5. And since 5 is the maximum, we update the value of 5 to 7.
You can use the green one. Maybe the green one is better.
To 7. And then we go to the next element, which is 7, and then we check the maximum from 5 and 2. And 5 is the largest, so that's the value over here would be 12. Then we do the same here, we choose from 2 to 6. 6 is larger, value becomes 10, and 6 likewise. Then we go to the row above this one, and 12 is larger than 7, so 12 plus 8 becomes 20. And 12, 13, is this 0?
Yes.
10. And then we go up to the last 23, 21. And then we do this 30. So the largest sum from top to bottom is 30.
Yes.
Anything else?
Yes, because I still feel this is very comfortable. Now that we found the solution, the maximum value, what if they also ask us to keep track of the path? Because in some of the dynamic programming problems, they might actually do that, you know? They might not just ask you the value, but also the way that you construct it. So basically, could you please return us a vector of pairs in which you're going to keep track of the path you took?
Yeah, it's just going to require using additional memory.
Yes.
So you want to that implement?
Yes.
With the green one.
With the green one, I think it's the best, but try this. Maybe that will. By the way, you guys should think about this too, like how we can keep track of the path efficiently.
returning the direction I, right?
Yes. Let's just return the direction array. But it should have the coordinates like. Yes, I mean if you just say 0 ones and then you just return me a two-dimensional array, that's gonna be too much of a work for me. So I just want to get the path. Like with indices, for example, you're gonna have like 0, 0, and then you get it from the left meaning 1, 0. Let me write the desired solution here. Like we start from 0, 0, right? And then we go to 1, 0. And then we go to 2, 0. And then we go to 3, 1. And finally we finish with 4, 3, right? Sorry, 4 ones. And if you finish this in a minute, I'm going to give you a new problem. Basically, at this point, by looking at the direction, you should be able to construct this, right? So is everybody able to follow what is going on here? So it's not just we are updating the value, but at the same time, we keep track of from which of our neighbors we get that value. So this way, once we finish execution, by following the direction array, we should be able to construct the path that is desired.
Only the maximum ones, right?
What's that?
Only the maximum ones?
No, I think like zeros and ones. I think 0 indicates if you just go down, and 1 indicates if you go down diagonally. But basically, we need to distinguish moves in our direction array here.
So the plan is to generate the direction array?
The plan is to generate the path. Like the direction array is the helper array that we are using here. Let me also populate this to make it clear. Zero index. This one is going to have 0 index. This is 21. So this one is going to have 0. Go down. This is 10, this is 10 too. Let's say this one that is from here. This one is going to have 1. All right.
So what I did is I created another table, which I called a pointer, which stores the directions that I go through each time I update the values of the rows and columns. For pointer at a row and column, if we go left from this, if for example we choose this path instead of this path, we store 0, and then if we choose the right path, we store 1.
Yes, like if we look at here, for example, once it is 0, it means just go down, and if it is 1, it means go diagonally rightward.
And once we finish computing the maximum sum, we go out of the loops, and then using starting from 0, 0, the starting column, we check the directions that we went through early on. For if at 0, 0, we went to the left, we must have stored 0 early on. So if it's 0, then we store, we update the column values. We don't update the column values, but we update the row values at every checkpoint. For example, at 0, 0, we went to the left, right? So the pointer value was 0. So first we store 0, 0, the first the starting row and column. Then we update the row every time. So it's going to be, the row is going to be 1. But since we went down, we're not going to update the column value. So it's going to be 1, 0. And then
Because the direction array or like the pointer array had 0 in it. 0 means just go down. 1 means go to right bottom. That's why we look inside, and if it is 0, we just go down.
yes. So each time we get a 1, then we update the column values to 1.
Mhm.
And
Let's execute on the example.
Okay. So we got a 0. We still have a 0 on the second row, so it's going to be 1, 0. And then on the third, we have a 1, so we go to the right, so it's going to be 1, 1.
2, 1.
2, 1, yes. And then we have a 0, so we just went down, so it's going to be 3, 1.
Wait, like after 1, 0, I think you still have 0 in it, so that's why you're going to go to 2, 0 first. Like the first one is 0, 0, we see 0 and we went to 1, 0, right?
Yes.
And then we see another 0, we went to 2, 0.
So it's 2, 0.
Yes, it's 2, 0, right? Right, sorry.
It was 2, 0 first, and then we went to 2, 1.
3,
1,
1, yes.
And then 4, 1, was it?
Yes, it's 4, 1.
This is the path.
Yep. So again, with the same time complexity, we were able to generate the direction array, and with the help of the direction array, or with the help of pointer array with your naming, we were able to construct the path that we desired for the optimal solution. So, thank you very much. Now you can get your feedback. So, is everybody clear with the solution here? Like how we generate the path? Yes.
Do we need the direction array, by the way?
Do we need the direction array?
Why not store
You
that
don't
in?
have to keep this as an array. Like you can keep it in a map, you can keep it in a data structure you want, but you have to keep this information somehow.
What if we just kept the actual index of that number?
What if we keep actual
Instead of
index
which
of that
direction
number?
back?
Instead of like using 0 and 1 here, you might write, for example, to this one, you might write 1, 0.
It would be a list though, since it's the passes it has passed so far.
What's that?
We'd save the list of the passes it's passed so far. For example, if we're at the bottom and then we go up, we choose which index I chose from below.
Yes. But in that case, you're going to have longer lists. Like, imagine for the second level, you're going to keep one list for this one list for this one. And here, you're going to keep one list for this one list for this one, and one list for this one. So basically, it means you are going to generate lists for all of them, and actually your space complexity is going to be worse.
Yeah.
Instead of the direction array, since we're updating the values on the main table, you can just choose the maximum of the two and keep going that direction. There's no need to use additional memory because of the two children.
You know which one is going to be the maximum.
Yeah,
that's
how
right.
you go the maximum.
Yes, yes. Yeah, you don't have to keep this. Like basically, what I was trying to say is you have to somehow be able to extract this information. It's either you can keep it in an array, or like you can, if it's easy to see from the updated values, then you can basically make use of that too. But conceptually speaking, it's going to be the same thing. If you consider multiple subproblems, keeping it might be more efficient. But that's a very good point. Like if they ask you to do it without extra memory, you can basically do it by looking which one is the maximum. Let me go there because the values are already updated. All right. Any other questions? Like, is everybody clear with calculating the optimal solution, not just that, as well as creating the path for the optimal solution? Because sometimes they might ask for the path as well. It's not just about the value. Sometimes they might ask about the path as well. That's why you need to be comfortable with both calculating the value as well as calculating the path. All right, if there are no other questions, thank you very much, Kaleab. And I'm going to add the DP problems soon. We have plenty of them, guys. Don't worry. And as always, we are going to finish with the code of the day. And this time, our code comes from Confucius. It does not matter how slowly you go, as long as you don't stop. Again, it's related with consistency. And actually, indeed, in this camp, we're not going slow. Like, we are actually going pretty fast. And as long as we don't stop and go pretty fast, amazing things are going to happen. And magics are going to happen in the camp. Thank you very much, guys.